Let's analyze and solve two-sum coding problem. In this problem, we are given a zero-based array of integers called nums. The array is unsorted. And we are also given a integer target. And our task is to scan through that array and find two values or two different positions in that array. Let's call them I and j, such that nums of I plus nums of j equals target. So we are looking for two indices such that the values at those indices, when sum, gives us a target. And that translates to the code where we have to write a function, and the function will have a parameter called nums, which will be a vector of ints, our array, and a integer called target. And the function will return a vector. This will always be a vector with two elements. These elements will be our I and j, or j and I, since the order doesn't matter. We are also given some additional constraints regarding the array size, the range of the values inside the array, and the range of the target. But the most important thing we are given is the assurance that in the input data, there will always be exactly one valid answer. So how can we solve it? Let's use our example array, which is 3, 8, 12, and 16, and try to think about the solution. So let's write down the indices first, 0, 1, 2, and 3. And the target is 20, equals 20. So when we look at that array, we as humans immediately can spot that the solution we are looking for is 1 and 2, because 8 plus 12 gives us 20, and the index of 8 is 1, the index of 12 is 2. So our solution would be the vector 1, 2, or the vector 2, 1. It doesn't matter which one we return because both are valid. The order doesn't matter. But this is only easy for us humans because this array is very small. If it had like 1,000,000 elements, we would be stuck. So we need an algorithm. And the first idea how to solve this problem is basically a brute force. We can try to find all the pairs of all the numbers in the array. And for each pair, we can compute a sum. And if the sum equals our target, that's how we can find the solution. So the way it would work is that we would start from the first element and try to go through all the other elements or the following elements in that array and compute a sum. So 3 plus 8 is 11. It's not our solution. 3 plus 12 is 15. It's not 20, so it's not our solution. 3 plus 16 is 19. Again, it's not our solution. That way, we just eliminated 3. So the 3 can never be a part of our solution. We would try the next number after 3, which is 8. And we don't have to check the past element because we already checked 3 and 8. So there is no point of checking 8 and 3. But we would check all the elements with the indices greater than the current one, so greater than 1. In this case, we would try first 8 plus 12, and fortunately 8 plus 12 is 20, so we just found our solution, and we would again return 1, 1 and 2, or 2 and 1, doesn't matter. And this solution is great, it works really well for small arrays, but for large arrays, the time complexity is not good. The time complexity is O of n squared, where n is the size of the array, n of n squared, because for each element we have to scan through the rest of the array. And as we know, this leads to quadratic time complexity. But the space complexity is excellent. It's O of 1. We don't use any other memory, any additional memory. So these are the complexity formulas for this solution. But we can do better. So let's try to think about a better solution. Again, we will start from the first element, but since we have to start from the first element because we have to scan through that array at least once. Otherwise, we would not know what are the elements in the array. So the way we will solve it is basically to scan through that array twice. The first time we scan just to create a map. So we will introduce the additional data structure, specifically a map or the unordered map in C++, but in general terms, it's just a map or hash map or dictionary. And we will store the following values. So the key will be the value inside the array, so nums of I, and the value will be the I itself, the index. So the first round, the first scan through that array would just populate that map. We would go like 3, the index is 0, we will move to next element, 8, the index of 8 is 1, next would be 12, the index of 12 is 2, and 16, the index of 16 is 3. So we just scanned through that array, and now we have all the values together with their indices in our map. After that, we would scan through that array again, starting from the first element. And for each of the elements we are scanning through, we would compute what is the element we need for this element to add to our target. So let's call this complement. And we would compute it basically by starting from target and subtracting the current value, so nums of I, which is in this specific example would be 20 for our first element. 20 minus 3 equals 17. So we need 17 in order to add to 3 to give us a target 20. So we computed 17. The next step will be to check, do we have a 17 in our array? So we would consult the map, and there is no 17 in our map. That means that 3 is not the solution. So we would move to a next element, which is 8. We again compute the complement for 8. It's going to be 20 minus 8 equals 12. Now we check the map. Do we have 12 in our map? Yes, we do. And the index is 2, and our index is 1. So we just found the solution, and we would return the current element 1 and 2. And the complexity of this solution is O of n. And the space complexity is O of 1, O of n again, because we have to store the entire array in our map. And time complexity is O of n because we have to scan through that array. Initially, we scan it once to populate the map, so it's n. And then we scan it again until we find the solution. So it's some constant times n, but we ignore constant. So our complexity is O of n for time complexity, O of n for space complexity. This is again a good solution, but we can improve it slightly, and we can improve it in the following way. So we will continue using our map. So let me erase everything. But the difference will be that we will not be pre-populating the map, but we will populate the map as we go. So the way to do it is like this. We start from the first element. We again compute our complement, which is 20 minus 3 equals 17. And then we do the same thing. We check, is 17 in our map? It's not. So the 3 cannot be a solution. But before we move to the next element, we will add 3 to our map. So 3, the index of 3 is 0. and then we move to a next element. And we repeat the process. So for 8, we will compute 20 minus 8 equals 12. Is 12 in our map? No, it is not. That means we have to add 8 to our map, so 8 and 1, and we will move to the next element. Now, and we repeat the process for 12, so 20 minus 12 equals 8. And we check, is 8 in our map? Yes, it is. So we just found the solution. The solution will be the current index and the index we found in the map. So we could return 1 and 2 or 2 and 1. It doesn't matter. So the difference is that in the previous solution, we had to pre-scan and then we had knowledge what else is in the array. In this solution, we do not have to pre-scan. We basically check each element with the past elements. And the benefit of this is that we have to only go through that array once, not twice as before. For this solution, the time complexity will be O of n, because we have to go through entire array. And space complexity will again be O of n, because in the worst case, we have to store the entire array in our map. And this is how we can solve this problem. Let's write a code for our solutions, starting from the brute force. So we are going to store the size of the nums in a constant. So const int size equals nums.size. And we will scan through that array. So for int I equals 0, I must be less than size, plus I. And for every element I, we will search for the matching element through the rest of the array. So we need another for loop. For int j equals, we have to start from the next one after I. So I plus 1, we start from the next one. J must be less than size. And we increment j, so plus j. And here we have to check if we found a solution. So if nums of I plus nums of j adds up to a target, then we found a solution. So we return I and j. And we should find a number here, the pair, because that's what we are promised in the constraints for the nums. But to avoid compilation errors, I will also return an empty vector after the for loops. So return empty vector, and this should never execute. This should never execute. And let's try to build this project. It compiled, and I have a 20 tests prepared for that problem. So let's run them. And all the tests are passing. So we have a brute force solutions written in C++. So let's now try to code the other solution using the map. So we will need to include an ordered map. And let's start from defining the map. So standard map. It will have int as a key and int as a value. Let's call it m. And the values, the elements in the array will be nums of I and I. And then we have to scan through the array again. So for int I equals 0, I must be less than size, plus I. We have to compute the complement. So const int complement equals target minus the current value, which is nums of I. And now for once we have a complement, we have to check if it is in our array. So if in our map, so if m that contains our complement, then that means we found a solution. So we can return, let's say we return the earlier index first. So m complement, which is the index stored for that number, and the current index, which is I. If it's not in the map, then we have to add a current element to the map. So we will basically do m of the current element is nums of I, and the value will be I, so the current index. And as before, we will return empty vector, but this should never be executed. And let's try to build this solution. It builds okay. And again, let's run the tests. All the tests are passing. So we just coded our two solutions. Let's make sure our solutions pass all LeetCode tests. So I'm going to paste the brute force first. And let's see if it works. It works. So let's try to submit this one. And it worked, but the time is not great as expected. So now let me copy the optimal solution, and let's try to paste this one and see how it works. So I will reset the current solution. I'm going to paste the one based on the unordered map. Let's see if this works. It works, and we can try to submit this one. And we got much better result with the unordered map as expected. That's the end of the solution. The source code is available in the GitHub repo shown on the screen.